This is Professor Scott Norman at Pittsburgh State University's Automotive Technology Department in the main automotive lab. The video that you're watching today is about burning or combusting methane, CH4, in an internal combustion engine. The students in the Automotive Technology program will all attend a mobile fuels class where we study the combustibility of many different fuels that you could burn in an internal combustion engine. Methane, CH4, natural gas, CNG is one of those. And so we study the combustion properties. We look at the stochiometric ratio as far as calculating that. We look at see how much CO2, how much water is produced by burning any fuel in an internal combustion engine. Hopefully you enjoy the video. Yes, methane, which is not methanol. It's not meth. When I talk about methane, it's natural gas coming out of your stove or something like that. So what's the chemical formula for methane? CH4. So anytime that I'm going to give you a fuel, propane, methane, all the basic fuels, there's only one formula. But when I get into gasoline, if I get involved in diesel fuel, I got to give you an exact formula because there's variations. And so, but CH4, okay, has carbon in it now. So now we have to deal with carbon. It gets a little bit more complex. I'm going to put this in my engine. What else do I need to put in that engine in order for combustion to take place? O2, yeah. So I'm going to put my O2 in here, and I'm going to burn it. I'm going to light my spark. I'm going to compress it. I'm going to light my spark plug. It's going to burn. So that's the process of combustion. And what's coming out of the tailpipe? H2O. Yeah. So the key is now I got CO2. So for all other fuels you're putting in the engine, and when I mean all other fuels you're putting in the engine, you got carbon in there. So it's a hydrocarbon fuel, and so we got now CO2. And CO2 is the normal output of combustion. Normal. You're going to burn wood, you're going to have CO2 and water come out of it. That's just normal. Again, the nitrogen that's in the air is inert. It's going to go in, going to not react to the combustion process. It's coming right out. So again, we'll talk about nitrogen and what happens when it gets too hot later on and issues with nitrogen. But right now, we're just doing perfect stoichiometric. So the first step in this process is to do what? Balance. So what do I want to start with first? Well, hold on. I don't want. Okay, so here there's more than one way to do all this. Okay, I'm gonna do it the way that I do it because as I'm teaching students, I just found that if you do it this way, it's easier than maybe other ways. You're like, oh, my chemistry teacher taught me this way, which is fine. I like to start with the fuel first. Start over here. Save the oxygen here for last because the oxygen's by itself. Okay, so when you have two here, it's a little bit of a harder problem. So let's start with the carbon. How many carbons do I have here? One. Okay, how many carbons do I have over here? One. Don't need to do anything with the carbons. One carbon in, one carbon out. So far, so good. I got 4 hydrogen in. So how much hydrogen do I have to have out? 4. So what do I do to get to 4? Put what? 2 in front of it, yeah. So don't change that to a 4. Now I have 2 molecules of water, okay? And so by doing that, so now what I do is I count up all my oxygen over here. How many oxygens do I have right here on this one? 2. Yeah, don't forget him. I have 2 of them, so I'm going to put a little 2 up here. And how many do I have over here? 2, okay. Which equals 4. So I got 4 on this side. So what do I do to get 4 on this side? 2 in front of it. So here's the deal. If the number of oxygens on this side is an even number, then that's easy. I'm just going to put whatever that is over here. If it's 10, I'm going to put a 5 here. If the number here is a 12, I'm going to put a 6 here and so on. That's really easy to do. It becomes hard if for some reason these two numbers is an odd number. For an example, let's say 7. Well, what do I do over here? Well, I can't, what do you say, 3.5 oxygen molecules, O2 molecules? You can't do that. Yeah, you have to double. So what you would do then is that if this oxygen number ever becomes a odd number, then what I got to do is I got to come over here and I got to say, okay, instead of only having one fuel molecule, I have to have a 2. And I put a 2 in front of there and I start all over again. So you're either going to have a single molecule or you're going to have 2. Those are your only 2 choices. So I'm just telling you, you're going to run into a situation at some point where this is going to be odd over here and you're going to have to double that and start again. So, which we'll practice one maybe next week, and that way you guys can see that process. So let's go back to this guy right here. It's not an odd number, it's a 4. So let's go back and look. I got one carbon over there. I got 4 hydrogen, 4 oxygen, 2, 3, 4. Does that look balanced? Okay, so let's now, what's our next step? Find the weights. Okay, so now I got carbon here. So what's my atomic weight unit of carbon? 12. Hydrogen is 1, and oxygen is 16. Hydrogen, 1, oxygen, 16, carbon, 12, oxygen. Okay, so again, there's more than one way to do this. I'm just making it a little bit easier. So then I'm going to multiply it by how many of them I have. So I only have 1 carbon there, so that is 12. I got 4 hydrogen there, so 4 times 1 is 4. Now the key here, though, is that this is CH4. So what do I have to do with these 2 numbers now? Add them together, and what are they? 16. So this is my total. This is an important number there. 16 times what? 4. And what's that? Huh? 64. That's an important number. How many hydrogens? 4, right? How many oxygens? 2. So what's my number here? An important number. Carbons I have is just 1, so that's 12. How many oxygens do I have? 2. 32 plus 12? Yep, I did that. Yeah, that's right. 44. That's an important number. So got 44, 36 for my water, 64 for my oxygen, and 16 for my fuel going in. Now, how do I make sure I didn't screw something up? Yeah, so what do I add together? 16 and 64 is 80. I'm just putting that in blue because that's just a check number. That's not something I use for anything else. What are these 2 numbers added together? Okay. So if these numbers are the same, you probably did not mess anything up. And I use the word probably because if I put a 10 in front of this and multiply everything out by 10, it's still going to be right. It's just going to be, the numbers are going to be a lot bigger. You know, they're going to be 10 times bigger than what you really need to do. Okay, so hey, am I finished or do I need to keep going? What's next? Break it down to 1 pound, because again, my fuel is in 1 pound increments for air-fuel ratio. So how do I do that?
Multiply the 64 by the 2, or no, that's 16.
Yeah, so I say that 16 equals what? Yeah, 16 equals 1 pound. Okay, so this equals 1. 16 equals 1. So how do I get this into 1 pound increments if 16 equals 1? Yeah, see how many times 16 goes into 64. So 16 divided into 64, and what's that number? 4. So the key here is that this number here that you're going to get is in pounds is going to be fairly low. 3 pounds, 4 pounds, 2 pounds, 1 pound. You're going to see those numbers fairly low. And if you got a big high number somewhere, you know, ooh, I did something wrong. So what's my, how many pounds of water do I have? Well, 4 divided by 36. And what's that number? Yeah, how many times will, I'm sorry, oh, wrong one. Oh, look what I just did. Oh, I almost did a mathematical error there. I'm grabbing that 4 there. I can't grab that 4. What do I have to grab?
16.
Yeah, 16 into 36. There we go. What's that number? Okay, so 2.25 pounds. And I'm going to start, that's an important number. I'm getting rid of this 80 because we don't really need it here for anything. And then for my 44, how do I figure that out? Yeah, 16 into 44, and what's that? 2.75. Okay, and that's pounds. So, what this all means, if I take 1 pound of natural gas, methane, I'm going to need 4 pounds of O2. And when I burn that, I'm going to produce 2.25 pounds of water, which is a lot lower than 9, where we got before, right? And I'm going to produce 2.75 pounds of CO2. I'm actually producing more CO2 than water now. Because that oxygen, that carbon is combining with that oxygen and CO2. And again, CO2 is natural. It's a natural process of combustion, so it's coming out. Okay, now, what's my stoichiometric ratio, though, for methane or natural gas? Either one. Compressed natural gas, you could call it different things. How do I figure that out now? Yeah, I got to know that there's 23.2% oxygen in the air. So only a quarter of the air I'm actually really being used for this combustion process. So you simply take and you put the 2 over, you put the 0.232, see how many times that goes into 4, and what's my number? 17.24 to 1. So that's my air fuel ratio at that there, is what it is. So is that slightly leaner or slightly richer than gasoline? Slightly leaner, yeah. So the compressed natural gas vehicles, that's a big thing right now, is that you're converting engines to run on compressed natural gas. That's happening in fleets all over the United States right now. And so like, well, why would you be doing that? Well, CO2 output is the big thing on this, because when we compare this to gasoline, you're going to see this number is quite considerably lower compared to gasoline. But also natural gas is a fairly consistent price, versus gasoline goes up and down, up and down, up and down, versus natural gas, you know, it's pretty consistent over the last decade or so. But this is slightly leaner, so I'd have to change my programming in my controller, because if I just kept it at 14.7 to 1, well, it's not going to be correct. Yes, sir?
So if we just need the 16 and the 4, then why do this over here?
Okay, because this is giving us other information. So the amount of water that I have right here in comparison, I'm not putting much water out of it, but this is how I'm determining high heat units and low heat units of how many BTUs this has. So I need the water output to tell me, hey, how many BTUs that fuel actually has. And if you look at the chart on 1-16, right now we're not necessarily doing that entire calculation. We're using a chart to figure that out. This is going to be determining my CO2 output, which is really a big deal right now. When you look at magazines, it's all about the CO2s or any type of articles. And if you're going to switch to a fuel, the reason why they're switching fuels, there's 2 reasons. Costs of that fuel, but also how much CO2 that vehicle is putting out. And so, and we talked about this earlier, that this number right here is a little bit deceiving. Okay, because natural gas doesn't weigh a whole bunch. And so if I'm just using this number by itself and not taking into account how much weight 1 gallon has in it, it's a little deceiving. And so how we compare CO2 output on vehicles is we do pounds per gallon. So here's the deal, is that stoichiometric is in 1 units of measurement, air fuel ratio in pounds or in grams, you know, versus CO2 comparison is in gallons. And so what I have to do is I have to take this number and I have to convert it into pounds per gallons. And so you need to know how much 1 gallon of methane waste, liquid methane. And so that's going to be a given. I don't expect you guys to know that, but that's a given. And if you look on that page that you're taking your notes on there, I should have given you a weight of that. 2.75. Okay, so it happens to be the same number, but that's just a coincidence. So 2.75 pounds for every gallon. So if I filled this gallon jug up full of diesel fuel, well, it's 7.1 pounds. Fill it up full of water, it's 8.3 pounds. If I fill it up with gasoline, it's 6.1 pounds. If I fill this up with liquid hydrogen, it's not even a pound. If I fill this up with natural gas, liquid natural gas, because that's the most densest, fill this up with liquid natural gas, it would weigh 2.75 pounds. So take this number, which is a given, multiply it by this guy right here, and what's your output there? What's 7.56 pounds per gallon. That's the amount of CO2 output you have. That's an important number because that's what you're going to compare with other people. Like if I told you diesel fuel puts 19 pounds per gallon out and gasoline produces 18 pounds per gallon, you see how people are switching to this, right? It's a big difference. If this was up close to 18, then you don't have a big argument of switching over because of lower CO2 output. But because that number is so low, and that is going to be the lowest number, the lowest output of CO2 is going to be methane or natural gas because it's the simplest. It's the simplest hydrocarbon. It has the least amount of carbon per hydrogen. Since it has the least amount of carbon in it, it's going to have the least amount of CO2 coming out of it. Does that make sense? Okay, anybody have any questions on this process of going through the calculations, just as we're kind of just going through it as a practice round?
Or you said water and carbon dioxide are the output.
Yes.
Is that always going to be like that?
Yes. Now, of course, you're going to have a different amount of water here and a different amount of CO2 here. And these numbers are all going to be different depending upon the fuel. But yes, if you take any hydrocarbon, which is pretty much everything except for hydrogen, and you burn it, you're going to get, if combustion is good, you're going to get water, you're going to get CO2. But again, what are some other, what else is coming out of the tailpipe? Well, you're going to get, are you guys done taking notes on this? So when you start looking at what's coming out of the tailpipe, besides these, you could get regular oxygen coming out if you're a little bit too lean. You could get hydrocarbons coming out. You could get CH4 coming out if you don't have enough oxygen. Or if you have incomplete combustion, the spark plug is not firing really good. You have raw fuel coming out. You have CO coming out, carbon monoxide coming out if you don't have enough oxygen or too much fuel. You have nitrogen coming out if everything is okay. If the engine, if the combustion temperatures get too hot, then we're going to take and we're going to steal the oxygen away from this guy right here. We're going to steal the oxygen away from this guy right here, and we get NOx instead of N2, which is NOx. Nitrous oxide, it's got to be, a smog agent. So when you look at what's coming out of the tailpipe, you have other things possibly coming out of the tailpipe if you start having problems. But if you have perfect combustion, the only real big number that's going to come out is CO2. Everything else should be very, very low numbers coming out. If you do a 5-gas analyzer, we can see those numbers. CO2 on a gasoline engine is up around 16%. If I measured the CO2 output of a natural gas vehicle, it's going to be a lot lower because there's less CO2 coming out. Did that answer your question? This is Professor Scott Norman from the Pittsburgh State University Automotive Technology Department. And if you're looking for more automotive educational videos, you could subscribe to my Professor Pintang YouTube channel. I also have a website, just look for ProfessorPentane.com. Thank you very much for watching.